Go now to our third speaker today, Joe Fox. Joe is president of Fox Consulting. He has extensive experience with industry, an active member of the Institute for Advanced Composites Manufacturing. He has been in industry for a number of years. We have worked with Joe in a number of projects, and great to have you here today, Joe. We're going to listen to your talk.
Thank you, Roberto. It's great to be back here again and have the opportunity to talk to you about decarbonization. And I want to thank both Reed and Roberto because I'm glad they went first, because they have had the opportunity to define a lot of the terms and acronyms that you're going to see in my talk that I won't have time to define. So when I came here last summer, I told you that decarbonization was a hot topic. And I think it's fair to say that it continues to be a very hot topic. It continues to be a very important part of a bigger conversation about sustainability. It's very clear that the current administration wants to lower the emissions of greenhouse gases, or GHGs. And they want to decarbonize many different industries. And the Department of Energy has actually developed a decarbonization roadmap to show how to do that. And the government is definitely putting their money where their mouth is. They are committing billions of dollars to the use of low carbon transportation materials, including more than $2 billion for infrastructure applications. And then you have the Department of Transportation. And one of their Everyday Counts, or EDC7 initiatives, is focused on reducing greenhouse gas emissions from infrastructure projects. And then you've got funding from the EPA. Last fall, the EPA announced a grant program focused on reducing embodied greenhouse gas emissions for construction materials and products. And I'm pleased to announce that ACMA and IACME have collaborated on a proposal that was selected last month to receive a $6 million grant from the EPA to help composite fabricators generate more of those environmental product declarations, or EPDs, that Reed just talked about. They call the partnership CIRCLE, and CIRCLE stands for Climate Impact Reduction through Composites Life Cycle Evaluation. And the purpose of the partnership is to show how emissions of CO2 and other greenhouse gas emissions can be lowered with composites. And there are both cradle-to-gate and gate-to-grave elements of that program. And I can tell you that as a result of this program, you are going to see many more environmental product declarations for fabricated composite products in the next several years. So I told you the title of my talk is An Important Equation for Decarbonization. And I'm not going to keep you in suspense any longer. Here is the equation. Okay? Concrete plus FRP equals lower CO2, or FRP equals fiber reinforced polymer. Now, it's not a very mathematical equation. You've got a plus sign up there, you've got an equal sign up there, and you've got a subscript 2, okay? But if you were looking for a differential equation, that's not what I'm showing you. But I want to show you in the next 15 minutes or so how using this equation can be a solution to lowering CO2 emissions. It can help you decarbonize your infrastructure projects. So I've given you the equation. Now I want to give you the take-home message, and I'm going to repeat it several times during my talk. But here's the message, that the use of FRP composites can lower embodied carbon and CO2 emissions in infrastructure and construction applications. Simple equation, simple message. And what I want to show you in the course of my talk is how this is true for both cradle-to-gate and cradle-to-grave emissions. But actually, I'm going to expand on this and say that it's really a two-part message, that there are two distinct sub-messages, if you will. And I'm going to talk about both of them. The first is that the use of FRP composites can lower embodied carbon and CO2 emissions in infrastructure and construction applications when they are used in place of steel. And the second part of the message is that the use of FRP composites can lower embodied carbon and CO2 emissions in infrastructure and construction applications when they are used in conjunction with concrete. And that's what I want to talk about today. So the first question you're probably asking is, why is it a two-part message? Well, to answer that, I want to show you this slide and talk a little bit about sources of embodied carbon data. And I'm going to tell you about multiple sources of that data. The first are these databases from the Carbon Leadership Forum. I call them the CLF databases. And they were published in 2021 and 2023, and they give you emission factors for construction materials like concrete, steel, and aluminum. These databases do not contain information for FRP composites. For FRP composites, you need to go to the life cycle inventories that ACMA has published in 2012 and 2023. And they give emission factors for composites produced with different resin systems and by different fabrication methods. And then there are things like Reed talked about, environmental product disclosures, like this one for FRP rebar here from Schock, a German company, and life cycle assessments like this one here for the Hillman composite beam, which I'll be talking about in just a few minutes. When you get into these databases, the information that you find is that they provide emission factors. And the most common emission factor units are kilograms of CO2 equivalents per kilogram. That's the most common one, and that's the one that I'll be using in a lot of these calculations. But it's not the only units, and you have to be very careful about the units, because for concrete, for example, it can be kilograms of CO2 equivalents per cubic meter. So when you're doing comparisons between materials, it's important to watch the units. And as Reed said, it's very important to do apples and apples versus apples comparisons. And that's what I've tried to do. So now I can begin to say, why is it a two-part message? And to do that, I'm going to show you some example calculations. And the first one that I'm going to do is FRP versus steel. So to calculate kilograms of CO2 equivalents, you need a weight and an emission factor. The emission factors come from those databases in the literature that I've just shown you. And I'm showing here the ones that I'm using for plate steel and FRP in this example here. Now, to keep the math simple, I'm going to take a steel part and make it 1,000 kilograms. So to get kilograms of CO2 equivalents, I need to multiply it by this emission factor here, and I get 1,470 kilograms of CO2 equivalents. Now let's do the same thing for FRP. And this is where the weight difference between steel and FRP becomes important, extremely important. Because instead of 1,000 kilogram part, FRP is 70% lighter than steel. So you only have a 300 kilogram part. And now you multiply it by this emission factor up here for vacuum infused FRP, and you get 780 kilograms of CO2 equivalents. That is 46% less than the example with steel. So the emission factor for FRP is higher, but the weight of FRP is much lower. And when you calculate that product, you get lower kilograms of CO2 equivalents with FRP. So this is sub-message number one, that you can use FRP in place of steel to significantly lower emissions. Now let's talk about sub-message number two. And here I'm comparing FRP versus concrete. Again, I go to the literature and get emission factors for the various materials. Now I'm sure that almost everyone in the room has heard somewhere that cement production is one of the largest producers of CO2. Okay? I've seen numbers as high as 4 to 8% of global CO2 production are associated with the production of cement. So it's true, but a lot of that has to do with the fact that the sheer volumes of cement that are produced every year. And remember, you don't build structures with cement. You build structures with concrete. And concrete is only about 10% cement. So the emission factor for cement is 1, but the emission factor for concrete is 0.1. And that order of magnitude makes a huge difference when you're doing calculations. Let's do one. Again, I'm going to take 1,000 kilogram part with concrete, but I only multiply it by 0.1 and I get 100 kilograms of CO2 equivalents. Now, let's do it for FRP. FRP is lighter than concrete, about 20% lighter than concrete, so I've only got 800 kilograms there. But then I have to multiply it by 2.629 and I get 2,100 kilograms of CO2 equivalents. That's 20 times higher than FRP. So replacing concrete with FRP does not reduce emissions. You need a different message, a very different message than with steel. And the message number 2 is that you can use FRP in conjunction with concrete to lower emissions. So at last year's meeting, a year ago, I gave this presentation, Decarbonization with Fiber Reinforced Polymer Composites. And I really told you message number 1. I showed you that emissions of CO2 could be reduced significantly when FRP composites are used in place of steel. So I'll call last summer's presentation Chapter 1, all right? And here's a summary of Chapter 1. This is a table that summarizes what I talked about last summer, because I compared GHG emissions for FRP and steel in 3 different applications: FRP rebar, FRP gratings, and actually the G-beam girders from AIT, okay? Now, I use data from the CLF database for the steel. I use data from ACMA and from EPDs for the data for FRP. And in the CLF database, they actually give 3 different levels for steel: achievable, typical, and baseline. And I compared FRP to all 3 of those. And this table summarizes the % reduction in greenhouse gas emissions possible when you replace steel with FRP. And I'm just going to focus on the middle column there, highlighted in red, because it's the typical values for steel. And what do you see? A 25% reduction for rebar, a 46% reduction for the girders, a 60% reduction for the gratings. All double-digit reductions in emissions when you replace steel by FRP. So if you summarize all this, and this was the take-home message last year, FRP has a very good cradle-to-gate decarbonization story to tell versus steel. And the main reason is that FRP is 70% lighter than steel. Now let's move to Chapter 2, different message. Emissions of CO2 and other greenhouse gases can be reduced when FRP composites are used in conjunction with concrete. And here I come to this very simple equation that concrete plus FRP equals lower CO2. And what I want to show you are 4 examples where you can lower CO2 emissions by using concrete with FRP composites. I'm going to talk about the Hillman composite beam, carbon pre-stressed concrete, the Halls River Bridge, and carbon cast. And in all 4 examples, again, I'm going to show you double-digit reductions in CO2 emissions when you use FRP in conjunction with concrete. And the reason is that by using FRP with concrete, you can significantly reduce the amount of concrete that you need. And when you need less concrete, you need less cement, and you generate less CO2. So let's go through those. But before I go through those 4 examples, I just want to show you this very useful figure from the 2023 CLF database. I really like this figure because it shows all the life cycle stages of a building material. You've got the product stage, the construction stage, the use stage, the end of life. Down here, you've got these arrows which very clearly define things like cradle to gate and cradle to grave. It also contains these alphanumeric terms like A1 and B3, which define the various steps in each stage. And I'm going to be using some of these alphanumeric terms as I go through the 4 examples. Excuse me. So first, let's talk about the Hillman composite beam, or HCB. How many of you have ever heard of the Hillman composite beam? Okay, quite a few people, all right? Well, there's a picture of a beam. There's a schematic showing the various elements of a beam. And the best way to describe an HCB is that it is a hybrid construction that contains embedded steel, rebar, in a concrete core and a thin outer FRP shell. So what you've got here is a beam that contains concrete, steel, and FRP. And it's the optimized use of each of these materials that gives you both tensile strength and compressive strength. And it also results in a lower weight, a much lower weight beam, because an HCB weighs 69% less than a precast concrete beam of similar size. In conjunction with RD Digital in the UK, CMSI, a Canadian fabricator, has conducted a life cycle assessment comparing a Hillman composite beam and a precast composite beam, PCB. And here is the results of that LCA. And this bar chart over here shows that what you've got is a 42% reduction in global warming potential in the amount of greenhouse gases when you use the Hillman composite beam relative to the precast composite beam, or precast concrete beam. You've got 15,000 kilograms of CO2 equivalents for the FRP or the HCB, and over 26,000 for the PCB. 42% lower. Why is that? Two reasons. Well, first of all, the cradle to gate emissions, those A1 to A3 emissions, are lower because the optimized design of the beam significantly reduces the amount of steel and concrete you need to produce the beam. And then secondly, you've got lower transportation emissions, or A4 emissions, because the HCB is 69% lighter, which means that it is much easier to transport to the construction site. 42% lower. Second example I want to talk about is carbon pre-stressed concrete, or CPC. This is a material, a technology that was developed by a Swiss company called CPC AG. And they have worked with Holcim, a big concrete supplier, to bring this technology to the marketplace. They've won a lot of awards in Europe for this. CPC uses high-strength concrete reinforced with pre-stressed carbon fibers. And it is used in applications like this pedestrian bridge and this observation tower. Now, exactly what is CPC? I must tell you, it has been difficult to find a very exact, concise description, but I found this paragraph in one of CPC AG's publications, and it says that CPC panels are reinforced with closed-meshed, pre-stressed carbon wire nets, and the carbon wires are pre-tensioned in both directions. Also, by going into their patents, I learned that the carbon fiber is used with a vinyl ester resin. So the P here, the polymer in FRP, is vinyl ester. Okay. Well, they say, I've also found these useful pictures, and they say pictures are worth 1,000 words. And I think these are, because this picture here shows the carbon fiber reinforcement in the concrete. And I would call this reinforcement microscopic in nature. I'm going to show you some pictures of some carbon fiber composite cables in a few minutes, which are much bigger, much more macroscopic in nature. The microscopic nature of the reinforcement is also shown here, where they're comparing the thickness of a CPC panel to the thickness of a piece of rebar. And the CPC panel is essentially the same thickness as a piece of rebar. So, how do you lower emissions with CPC? Well, the use of those carbon microfibers to reinforce concrete enables you to make the concrete much thinner. And that significantly reduces CO2 emissions. Less concrete, less cement, less CO2. And they use this example of this footbridge in Switzerland to make that point. If you make this footbridge with traditional reinforced concrete, it would weigh 56 tons. When you make it with CPC, that same footbridge weighs 14 tons. That's a 75% reduction in weight. You're reducing the component CO2 footprint by up to 75%. 75%, double digits. Third example I want to talk about is the Halls River Bridge. This is located in Homosassa, Florida, north of Tampa. It's a continuous deck with 5 spans. It was completed in November of 2019. You see a picture of the bridge there. This was really an experimental project by the Florida DOT. They used all kinds of innovative materials in this bridge. Many of them were FRP. They used GFRP rebar. They used these carbon fiber composite cables, which are the macroscopic cables I talked about a few minutes ago, much larger than those carbon wire nets. And they used Hillman composite beams. The main reason that they used FRP for this bridge was the corrosion resistance of FRP. This bridge exists in a very corrosive environment in Florida. So this is an article in Advances in Civil Engineering Materials. The authors are Thomas Cadenazzi, Tony Nanny, who was a professor at the University of Miami, who was Thomas's PhD thesis advisor, and Steve Nolan from the Florida Department of Transportation. They have conducted the most comprehensive life cycle assessment, LCA, and life cycle cost analysis, LCCA, that I have seen for FRP in an infrastructure application. We could spend an hour going through this publication. Here's the Cliff Notes version. Their LCCA showed that the net present value of the life cycle cost is 20% lower with FRP, primarily because of reduced maintenance and replacement costs. That's another very good story for FRP, but that's a story for a different day. Their LCA is relevant today because their LCA showed that cradle to gave emissions are 26% lower with FRP than with steel. Again, double digit. And here's the data that shows that. These are tables taken from their report where they're looking at the kilograms of CO2 equivalents, cradle to grave. This is the data here for the FRP bridge. Here is the data for the steel bridge. And if you compare this number to this number, you see that the kilograms of CO2 equivalents are 26% lower with the bridge made with FRP. And if you go across the rows, the emissions are lower at every stage. Last example I want to talk about is carbon cast. Carbon cast is a precast concrete that is used primarily for construction applications, not so much for infrastructure, construction applications. And there are a group of precast concrete suppliers known as the Altus Group that use carbon cast to make insulated wall panels and architectural cladding in the buildings that you see on the right. Carbon cast uses a material known as C-grid with concrete. And this is a picture of C-grid. It is a flexible grid that consists of carbon fiber in an epoxy matrix, and it is supplied by a company known as Schomerod. How does C-grid work? What does it do? It serves 2 functions. It is a low thermal conductivity, high strength connector between 2 concrete widths. And basically it is a truss, this green truss here, that extends through the insulating foam between the 2 concrete widths. Okay. It is much lower thermal conductivity than a steel connector, so it helps the insulating properties of the building. And then it can also serve as a reinforcement for a concrete width. In this schematic down here, it's actually serving as a secondary reinforcement, these green dash bars, and FRP rebar, rebar is the primary reinforcement. So 2 different functions. This is a picture of a data center in a recent announcement from Metromont. Okay, Metromont is one of those precast concrete suppliers in the Altus Group, and they use carbon cast and C-grid in data centers. And what they say in this press release is that the amount of CO2 can be reduced by 40%. Okay. Again, less concrete, less cement, less CO2. Now again, carbon cast is used primarily for construction applications. But if you look at this picture, everywhere around me, they seem to be building these data centers, everywhere. And so I would make the point that these data centers are a very important part of our communications infrastructure. So now I've shown you 4 examples of double-digit reductions when concrete and FRP are used together. So I'll come back to my take-home message one more time, that the use of embodied FRP composites can lower embodied carbon and CO2 emissions in infrastructure and construction applications when they are used in place of steel and when they are used in conjunction with concrete. In place of steel, I've shown you this table with double-digit reductions for things like FRP rebar, FRP girders, and FRP gratings. And a lot of that has to do with the weight reduction. And then I've shown you today in chapter 2, 4 examples where once again you see double-digit reductions in the amount of CO2 emissions. And the reason here is that you're reducing the amount of concrete. So that takes me back to the simple equation. The simple equation is concrete plus FRP equals lower CO2. And that's what I'd like you to take away from today. It all amounts to, if you use FRP in the right way, you can lower the amount of concrete, you can reduce the amount of cement, and you can reduce the amount of CO2. So if you want to decarbonize your infrastructure projects, I'd like you to remember this equation. And that concludes my presentation.